All right, so we just talked about some of the non-enzymatic changes that occur when we're exposing plant tissues to heat. One of the most dramatic effects that we see is tissue softening, and a lot of this has to do with pectin being lost or being depolymerized. And remember that pectin is the glue that holds all these cells together. So we're seeing loss of cell adhesion, and sort of the net effect of that is softening. That's how we perceive it. We also talked a little bit about enzymes as well. We talked about two key enzymes that are important in terms of pectin stability, polygalacturonase and pectin methylesterase, so PG and PME. And remember, I told you that PG was the enzyme that would cleave the glycosidic bonds that links all these galacturonic acid units together. So here's pectin again. Remember, here we're just showing 5 subunits of pectin, but this is a large polymer. And PG comes in here and will cleave these bonds and take a large polysaccharide and turn it into smaller fragments. Okay, and that's really the basis behind the loss of cell adhesion in plant tissues. So PG will do this, but PG only does this when it can access pectin. So under normal conditions in the plant cell, PG and PME and other enzymes that can degrade pectin are separated, physically separated from the pectin. And it's only that when we decompartmentalize those two things, the substrate and the enzyme, that the things can react, and that these reactions can occur. So a really good way to introduce PG, an enzyme like PG, and pectin, the substrate that pectin that PG works on, is to physically or mechanically disrupt the tissue. What do I mean by that? So let's use tomatoes as an example. We'll be processing tomatoes in the next couple weeks and talking about these concepts in more detail. But let's say you took a whole tomato and you chopped it into small pieces. Those would be conditions where the enzymes and the substrates are decompartmentalized, that they can come into physical contact, and that PG can come and start acting on pectin. So you'd have these small little chunks of tomatoes here that would become increasingly soft because you've got all these active enzyme reactions occurring, including PG. PG is working on pectin. You're getting depolymerization of the pectin, and cell adhesions going down, softness is going up. And if you're to take those chunks of tomato and do a further heat process, like if you were to put them in a can and put them in a steam retort, as we'll be doing in lab in a couple weeks, these would just turn into mush. They'd all fall to pieces. So a really good way to prevent that is to do a process called hot break, and that basically entails taking the whole tomato. So here's a tomato. Adding heat to the whole tomatoes. So we haven't chopped up this tomato yet. We haven't allowed PG to come into contact with pectin yet. Everything's still in its compartment. We're going to heat this up quickly, and what's going to happen is that we're going to thermally denature PG. So PG is going to be denatured, basically. It's going to be destroyed, and that's going to lead to increases in firmness of the final product because we're maintaining cell adhesion. Okay, so we're thermally denaturing PG. Okay, and now we can go and chop those tomatoes. And we get little chunks now. We've mechanically disrupted all those cells, but it doesn't really matter now in terms of firmness because we've destroyed the enzyme that can work on pectin. Okay, so this is a process you might see this sometimes. We'll be talking about this in lab. It's called hot break. So PG is really the enzyme Polygalacturonase is really the enzyme that we associate with losses of firmness of tissue. So PG is active, we're depolymerizing pectin molecules. We don't associate PME with these changes that affect texture, but actually PME can have a really profound effect on texture, and we can actually take advantage of PME in processing to increase the firmness, to preserve the firmness or increase the firmness of tissues. Okay, so here's an example of a way that we can use PME to actually improve the texture of a plant tissue to maintain firmness. So again, let's take a tomato as our example, as we did before. Take those tomatoes, we're going to chop them up to little pieces, just like we did before. But now we're going to take some calcium chloride and we're going to add that to these tomatoes. We're probably going to do this in a container. This can be a can, this can be a process vessel, it doesn't matter. So now we've got our tomatoes and our calcium chloride, but really the important thing here is the calcium that's doing the work. And we're going to let that sit there at room temperature or slightly above for a certain amount of time. And these are good conditions for PME to work. So PME is active under these conditions. Remember that we've taken our whole tomato, we've chopped it up. Now we've got physical contact between the enzyme PME and the substrate pectin. So it's going to work. And remember, what's happening here as PME is working is that we're taking methyl groups and we're converting them to carboxylic acid groups. And under the conditions, so it's going to be this plus a certain fraction of this, so the protonated version and the dissociated version. Under the conditions that we're working here, we're going to mostly have this right here, this species. And what's happening is that here's one pectin molecule, here's another pectin molecule. These can now be cross-linked by calcium, which is a cation, a divalent cation, 2+. So two positive charges can link two negatively charged molecules. Okay, so imagine you had this happening all over the system. If this is your pectin molecule, you're going to have these little sites of negative charge all over it. Here's another pectin molecule. This is a very simplified schematic of this. Now you've got these little calcium bridges that link up all these pectin molecules together. And the net effect of that is a very stable, very strong, very strong structure. Okay, and this leads to a preservation, or in some cases an increase in the firmness of the tissue. So you're probably asking the question, why do I need PME to be active here? Why don't I just add calcium? Well, the simple answer is that calcium works a lot better to provide these, to form these cross links if PME has been activated in advance. So here's an example of what I mean. Here's a situation where we've got some pectin in a plant tissue, and 75% of that is in this esterified version. And esterified meaning that it's got the methyl ester groups on it. And only 25% of it is in the form of these carboxylic acid groups. So if you're to add calcium chloride to a tissue that had this kind of pectin profile, you only really have one opportunity, at least in this slide, to cross-link these two different pectin molecules. So here calcium comes in, it's able to electrostatically form these cross-links to calcium here, but calcium has no effect, has no way to interact with these molecules here. However, if you let PME do its job, you're going to convert a lot of those methyl ester groups to carboxylic acid groups. So before, remember I showed you, this is the before situation where we had only 75 or only 25% of the carboxylic acid groups that could participate in these calcium bridges. Now we let PME do its job, and we've got this kind of situation where 75% of the groups are the carboxylic acid groups. And in the presence of calcium, we can form, at least in this example here, 3 bridges. So at the risk of sounding repetitive here, I think this is a good way to schematically understand what I'm talking about, the importance of PME and calcium chloride. So if we've got a situation where we don't have PME active, we're going to have a form of pectin which is called the high methoxypectin. So a high amount of the pectin is going to be the methyl ester pectin with a very low amount of the carboxylic acid groups. And remember, those carboxylic acid groups are the important ones to have because they're the ones that interact with calcium to give you those cross bridges. If we have that situation where we have a high methoxypectin and a low amount of those negative charges, when we add calcium, we're going to have some firmness. We're going to have some tissue maintenance there, but it's not going to be as effective as if we started with low methoxypectin. And the way that we go from high methoxypectin to low methoxypectin is to add PME. And PME converts high methoxypectin to low methoxypectin by converting those methyl esters to carboxylic acid groups. If we add calcium to that situation, to that system, now we can form a lot more of these crosslinks. So if you've ever gotten a can of tomatoes, you looked at the ingredients and you wondered why is there calcium chloride added, this is the reason why. We're adding calcium chloride really for the calcium, and that calcium is used to bridge pectin molecules that have negatively charged carboxylic acid groups. So just to illustrate that this is not ancient history, this is actually relatively new science, and this is a great example of food science research. This is an article published in the Journal of Food Science in 2005, showing how PME can be activated in the presence of calcium chloride to improve the firmness of diced tomatoes. Here's some data from that study showing how calcium and PME affect firmness. Here on this y-axis, we're looking at force. So this is force as calculated using a texture analyzer, like the one that we've got in the teaching lab, like the TAXD2. The more force it takes to cut through one of these tomato chunks, the firmer the texture, so it's a way of measuring firmness. A higher value in force, as measured in newtons here, means firmer texture. So in this study here, the researchers took some diced tomatoes and added a set amount of calcium chloride, 0.5% calcium chloride, to the brine solution, and let those tomatoes sit at temperatures ranging from, let's say this looks like 22 degrees up to 90 degrees Celsius, centigrade. And you can see even at low temperature, so this is below really the activity, the optimal activity range for PME, the addition of calcium increases the firmness slightly, okay? And I'm going to refer back to this, hold on. So in that situation, they're starting with probably high methoxypectin, they're adding calcium, and they're getting some increase in firmness just because calcium's able to interact with the few carboxylic acid groups that are present. However, if they take those cans and they expose them to higher temperature in the range where PME is most active, so it's this range right here, at least according to this study, between 16 and 80 degrees C, we see the greatest effect in firmness. And that's because we're allowing PME to really work and to convert a lot of the high methoxypectin into low methoxypectin. We're getting a lot of these charged pectin molecules now and in the presence of calcium chloride, we're able to form lots of these cross links. And again, the effect of that is increased texture, increased firmness. Another figure from that study. Remember I told you that a key product of PME is PME activity is methanol. Remember that we're starting with methyl esters. PME is active. We're converting these into these carboxylic acid groups, and we're also getting methanol as a product of this reaction. So a way that the researchers in this study followed this reaction was to measure the amount of methanol that's being produced. And remember, go back one slide here. There's not much happening in terms of PME activity in this temperature range between 22 and we'll call it 60. And the way that they knew that is because they looked at firmness. Another way that they confirmed that PME is what's acting here is by measuring methanol concentration. So here's methanol. We can see we're not getting a lot of methanol until we get to the point where PME is active. The temperature range, the optimal temperature range for PME. So I've been talking a lot about tomatoes here, but this chemistry is relevant in other foods as well that we thermally process. Here's some examples of some potatoes where the texture of the potatoes after canning has been improved by the addition of calcium chloride. So if we just take regular potatoes and we pack them into cans and we cook them, thermally process them, we often see this situation here. Lots of breakage, loss of quality. If we activate PME and we add calcium chloride, we can get something that looks more like this, something that's a lot more acceptable. And this is described in this study here by Dr. Laborde, a professor in our department and a collaborator at Cornell, showing that calcium chloride and PME activation in canned tomatoes can increase the quality of those potatoes.